A simple statement related to graphs. We are going to prove this statement using induction. There are 2n, even number of points altogether, n squared plus 1 line segments are drawn between them. So it's kind of graph, and then you connect some of the points. And then the number of connections is n squared plus 1. Show that there is at least one set of 3 points which are joined pairwise by line segments. So we need to prove that there is a triangle. Let's see one example. For the number of points are, let's say, even 2 points. If you start with 2 points, it's impossible to have a triangle, so just skip this case. Let's start with 4 points. And then when we have 4 points, n would be equal to 2, which means 2n is 4, n squared plus 1 is 5. If you do 5 connections, then you will have a triangle. So I could go like this. 4 is not enough, because if I do something like this, 4 segments, this one doesn't have a triangle. So three points that are, so if you take these 3, it's not connected here. If you take the upper 3, it's not connected here. So any 3 are not connected into a triangle. So we have 4, and when I add the 5th one, there will be a triangle. So in total there are the complete set full graph will have 6 edges. So 5 is enough. So now comes to mind why the n squared. So this is just like kind of first analysis of the problem, right? So why it's n squared? So since we have 2 endpoints, from here you can see that n squared, the reason why it's n squared, you can split the points into 2 parts. Let's say when n is equal to 4. Let's say 4. Imagine this graph. So put 4 points here, 4 points here, and connect every point from the left to every point to the right. Something like this one connects to all 4. This one also connects, and then this one also connects to all of them. And we have 4 multiplied by 4, basically 16 lines. So if you connect all 4 from the left to all 4 to the right, you'll get 16 lines, but there will not be any triangles, because since these are not connected to each other, we need a triangle where 3 points, all of them are connected, right? So every 2 point, like end of every segment is one of them on this side, the other one is on the other side. So 2 of them will be on the same side, but they are not connected, so we don't have any triangles here. So if you add one more, if you do +1, if you do 17 here, 17, then you'll need to connect one of these 2 points, like on the right or left, and then that will give you a triangle. So a bunch of triangles actually. So that's why this is where the n squared plus 1 comes from. So instead of for this problem, so instead of doing induction on this exact statement, we can do induction on the contrapositive of this statement. So we can prove that when there are 2 endpoints, the number of line segments between these points is maximum n squared in order not to get any triangles. So without triangles you can have maximum n squared. So when you have n squared plus 1, which means like when you add one more, n squared plus 1, you'll have a triangle. So that's kind of the idea. So the statement, the new statement is the following: n squared is the maximum number of line segments without triangles. So if I use the induction to prove this statement, so the base of induction will be obvious. If you do n is equal to 1, n is equal to 2, that's kind of obvious. Probably it will be easy to check. You can just proceed to the step of the induction. And then assume that for 2k points, there are maximum k-square line segments without any triangles. So this one is without triangles, not segments. And then we will need to prove that 2k plus 2 k plus 1 square, right? Now imagine 2k plus 2 points, so a bunch of points. The number of them is 2k plus 2, and then some of them are obviously connected. So let's choose 2 points which are already connected. So let's say A and B, they are already connected. So we have the connection here. And these A and B are connected to some points, right? Somehow connect to some of the points. So now if you remove A and B and all related segments. So if you remove A and B and remove all related segments, you will be left with 2k points. So this part of the graph will have 2k points, this part. And if I try to make if I try to do line segments, if I try to draw line segments without a triangle, I will have maximum k-square by the assumption of the induction. And so this k-square, we have maximum of k-square here, and then if I add back these 2 points A and B, since they are connected, I will have k-square plus 1, and there will be so like if you take any point inside these k-square points, A and B, they cannot be connected to this point C at the same time, both of them together. So only one of them will be connected to any point. So there are 2k points, and to each of these 2k points there will be maximum A or B. One of them will be connected. So which means I can have maximum 2k more line segments. If it's less than 2k, it will be less, but I can have 2k line segments. So which is if I rewrite k plus 1 square, k plus 1 square. So which means, which kind of proves my assumption. If I have 2n points, the maximum number of line segments without triangles is n square, which means if I have n square plus 1 points, there will be a triangle. So, and altogether, which kind of proves my original statement, at least one set of 3 points that are pairwise joined. So in this problem, instead of proving the statement directly, which we rephrased and then made another statement, which is easier to prove. When you prove it by induction, you get the result of the original statement as well.